Now, let's look at what a schematic is. Let's start with something you already know. Let's start with a blueprint. Some of you may have seen a blueprint. Some of you may have seen something you thought was a blueprint that really wasn't. Maybe you've been to model homes. You're shopping for homes with your parents, and you walk into the model, and they give you that little floor plan. Shows you where all the different rooms are. And Matt goes, oh, I want that room right there so I can sneak out at night because it's away from my parents and I can crawl out the window. Something like that. I don't know. You know that the drawing you see of that house, of those rooms, is not the way it actually looks in real life. It just represents things in real life. The door in real life is not just a slanty line, but that shows you where it's going to be. Now, a floor plan is a very basic drawing showing you where things are going to be. It doesn't have a lot of detail. A blueprint has more than a floor plan. It has more detail. And they're big old sheets, you know, that you'll have multiple pages. Has anyone actually seen blueprints in here before? Okay. Maybe your mom or dad is an architect. Maybe you saw blueprints for your house you're going to build. You're going to have a page for each kind of thing that they're doing. Now the pages look a lot alike because they all have, you know, the same basic outline for the walls and the rooms, but they'll have different information depending on who that page is for. If the page is for the framers, those are the guys that put up the wooden beams that they attach the drywall to. It's going to tell them dimensions. It's going to show them where they're supposed to put the door, how wide the door should be. There's going to be measurements on there. If the page is for the plumber, it's going to show where the sink and the tub and the shower and all that goes, and where the water lines go, and the hot and the cold water. If it's for an electrician, it's going to have symbols like you see up here, all sorts of different symbols that tell them what kind of outlet needs to go where the switch is going to be, what switch controls what. So in that picture, you have a lot of information. It tells you the parts that need to go into making that thing. It describes them. So it might say what the dimensions are of the tub. It might say the brand. It might tell you all sorts of information about it. So you'll have not just the parts, but where they go, how they all go together, and their specifications, their specs, we say. What are the dimensions going to be? And you'll have one, like I said, for electricity, one for plumbing, a page for the framing, for each of the different areas that have to be constructed. Okay? So that leads us to an electronic blueprint. An electronic blueprint is called a schematic, and it's used to show, and I'll give you the definition here in a second, it's used to show you not just what parts go into that circuit, but how they are hooked together, how they are wired together. It's like a recipe, and I'm going to show you these symbols. We're going to learn the symbols, we're going to learn what parts go with those, and how the parts work, what they actually do in the circuit. And once you know that, it's a very cool skill to have, because it's like being able to read a recipe. If you can read a recipe, if you know what mix versus stir versus flambe versus blend, all these different cooking terms, you know what a cup and a teaspoon is, you can cook anything. You can follow the recipe, you can cook anything. That's pretty cool. If you know what these parts are and what this picture is telling you to do, you can construct any circuit. You don't even have to know how it works or why it works. I don't have to know what makes a recipe tasty. I can just follow the directions and do what it says and hopefully get good results. So we use these kind of technical drawings all over the place to represent things. It's much easier to have a picture than it is to have words. I could describe to you in words how to make this circuit. Oh man, let me tell you, that would be a lot of words, and it would be confusing. By showing it in one picture, it's so much easier. So over here we had meters and dimensions. Over here we have labels for the different parts and what they do. Now I know you don't know what any of these are yet, but eventually when you know what this represents and what these represent and what the little labels are, it's easy as can be to build a circuit. There's not a lot of knowledge you have to have. You may not be an engineer and be able to explain why it works, but you can do it. This guy down here, let me zoom out. This guy down here is a drawing of some sort of device. I don't know if it's a motor or a pump or just what, because I'm not a mechanical engineer. But if your mom or dad is, they could look at that and tell me exactly what that thing is, what it does, and what all the numbers mean. So we use these in a lot of different areas, not just electronics. In electronics, a schematic is a blueprint that shows you the parts and how they go together. So your definition will go something like this. Schematic is a technical drawing which describes the parts and how they are connected. A technical drawing which describes the parts and how they are connected. A schematic is a technical drawing that shows the parts and how they are connected. So in this blueprint here, what part's that? What is that? Toilet, what's that?
Sink.
Bathtub, what's that? Sink. And that's not the way they look in reality, but it represents it. In fact, they use different symbols than what you see here in a real blueprint. These are the actual symbols they use for these different electronic parts. And it may be like, well, that doesn't make any sense. Why would they draw it like that? There's actually a reason, and it does make sense why they draw the symbols the way they do. And you'll see with the ones we'll go over today. And it does kind of make sense when you understand these things, why they draw the symbols the way they do. These are some symbols, some schematic symbols you've already learned. And since we know how these things work, how they function, what goes into the parts, it makes sense. You know this symbol. If this were a blueprint of a house, what would a line represent? A wall. So that would be a wall if this were a blueprint. In an electronic circuit, it represents a wire, a conductor. What would this be then? A wire. What would this be? What would this be? A wire, okay? Don't get thrown off. Just because it's going in different directions, it's still a wire. Now, we don't typically draw schematics with lines like that. As you saw in the previous one, we make our schematics with a ruler, nice and straight. Sideways, up and down, nice and straight. It's easier to read that way. But it can be drawn that way. It would still represent a wire. Just because it's sideways or at an angle doesn't change what it is. Electricity doesn't care whether it's flowing, at an angle or this way or that way. It's the direction that's important. If this were a house and a blueprint, what would that represent? A door. In fact, they might even do, little dots like that to show you the way the door swings. Okay? Well, this in our circuit, in an electronic circuit, is a switch. What's that? Switch. What's that? Still a switch, okay? Not every switch is drawn exactly like this. There are different types of switches, depending on what they're doing, depending on how complicated, how many things need to be switched on and off. You have other switches that look different from this. This is the most common kind. That's the switch like we have here on this wall plate. But not all of them are drawn sideways like this. We could draw it over here and it's going to be the same thing. We could have little dots here and it would still be a switch. Okay? But this is the most common kind. The next one here. Battery. What kind of current do we get from a battery? Direct current. DC. So we may be getting that directly from a little battery through a chemical reaction. Or we may be getting it from an AC adapter. Remember the black box? For a star, who can tell me what two things are found inside an AC adapter? Nobody could do it last period. Jeff?
Transformer and diode.
Close. Not a single diode, but
Oh, four.
four. And what do we call four of them hooked together like that? If you have it in your notes, you can look if you find it.
Is it? It's either series
What's the name of that device that turns AC into DC? What's the thing called that changes the voltage, makes it higher or lower? Transformer. What's the thing called that turns AC into DC? Rectifier. You got it. You stole it from Jeff. Okay, rectifier. Remember the rectifier is the thing that takes, here's my AC like this, right? It takes this part here off and it puts it up here. You guys remember this?
Yeah.
Okay. So an AC adapter can also give you this kind of electricity, and we might draw it that way. But typically it's a battery. Remember now, in our homes, most of the electronic devices, from cordless phone to cell phone to clock radio to stereo to DVD player, computer, they all use what kind of current? Direct current. So that means that the electricity that comes out of the wall has to be changed. So the direct current, understanding that direct current flow is real important to you guys because that's what most of our devices run off of. You know, a hot plate doesn't need direct current. A single light bulb in a lamp doesn't need direct current. Can run directly off of the AC. We don't have to make any changes. But most other things need this kind of flow. Now, does it make sense that they draw it like that? What do you think this and this represent? Negative and positive what? What are these two plates called? You can almost picture our little battery that we built. Electrode, yeah, with a little electrolyte going through there. Okay, so that's what those two lines represent. So it actually does make sense that they draw it that way. Instead of a pretty little picture of a battery, they use these to show me the two plates. And we know one of them is always going to be positive and one's going to be negative. Okay? If I draw it this way, it's still a battery, even if I draw it sideways. Got it? Okay. Last one. You've seen this one before, but I might have drawn it slightly different. Sometimes you'll see it drawn differently. Zach?
Coil?
Well, it is a coil, but it's surrounded by some circle thing. Jeff?
It's a light bulb.
It's a bulb, a lamp, a light bulb, whatever you want to call it. And you know that a bulb or a light bulb or a lamp has a little, what's the little wire called? Filament inside. That's what that represents. You may see a light bulb drawn, you know, like this. It's still a light bulb. Okay? Now, there are some other symbols that we have covered. We have covered this symbol here with no circle around the outside. What's that? Coil. Then if I add another one next to it like this, what's that? Oh, stumped you guys. We totally blew off one of these lectures, huh? It's the same one where we talked about the rectifier. What is it? Primary and secondary coil on a, what's this whole device called? Heard someone say it. Say it out loud. Transformer. This is the transformer. Remember we drew 3 different kinds. One that increases the voltage called a, one that decreases it, one that doesn't change the voltage, isolation. So that's a transformer. Sometimes transformers have little bars in between like that. It's still, well, you got that right. It's still a transformer, okay? But if you just have one of them, then we call it a coil or a choke, that you were talking about, okay? So there are different ways to draw these things. Now there's one other symbol that I can think of that we have covered, like that. That's not a light bulb. What is that? What does that mean when you see that symbol? AC. So when I start drawing circuits, like you guys had a circuit drawn on the board for you over there, a schematic, to do your fishing rods. And your fishing rod ran off of a battery, direct current. So you would have this kind of thing here, and you had your coil of wire, and then you had your switch, like so. Okay? Recognize that? So you close the switch and electricity can flow through the coil, creating, what do you get when you run electricity through a wire? You get magnetism. But I could replace that supply of electricity and I could say that's coming from AC. AC. So this means the supply is coming out of a wall outlet, alternating current. Or from, what's the device called that makes that kind of current? Generator. Okay? So those should be pretty much all the schematic symbols you've learned so far. You're going to learn even more, but those are just the beginning ones. You got to know those to be able to look at the circuits we're going to look at here next. You got to know these rules too. Now we kind of covered these before, but I would write them down again in your notes. These are the rules for electrons. If you can think like an electron, you can predict what it's going to do, where it's going to flow, and why. And the electrons will follow these three rules. Rule number one, if we're talking about direct current, like I said, that's what most complicated electronic devices need, the electrons are only going to travel forward. They will never go backwards. Any more than your stick of dynamite will explode twice, or your battery will die and suddenly come back to life without being recharged. They only go forward in one direction. Second rule. Why did the chicken cross the road? To get to the other side. Why did the electron travel through the circuit? To get to the other side. The goal of the electrons in that circuit is to get to the other side of the battery. You look at this. I can make a simple circuit out of this battery pack. By simply connecting these two wires together, I now have a complete loop. The electrons will flow from one side of the battery through the wire to get to the other side of the battery. Because it's following that basic rule of science. Opposites attract. The pluses and the minuses are attracted to one another. And that's why the electrons want to go to the other side. That's why the chicken crossed the road, to get to the other side. Third rule, electrons will take the path of least resistance. Notice I said path of least resistance. I didn't say the shortest path. Nathan, what's the path of least resistance for you to get out of this room? Yeah, down the aisle and then across this way. The shortest path would be straight line. Hopping over the desk and running over the trash can to get to the door. Obviously, it's going to take a lot more energy to do all that. Why would an electron waste energy going a harder way? It wouldn't. Any more than a ball will suddenly roll uphill, you're not going to take a harder path. You're going to take the easiest path. Nature is lazy. It's going to take the easiest path. Water is going to take the easiest path flowing downhill. The electron is going to take the easiest path through the circuit. If you keep those three rules in mind, you'll be able to predict where the electricity is going to flow and do a lot of cool things. With this little bit of knowledge today about these circuits, you can predict a lot about what's going to happen in these different situations. So we're starting with some real simple circuits. We got a couple of light bulbs, maybe three, and we've got, what's this? Battery. Okay? Right now, I have what's called a closed circuit. That means there's a complete path for the flow of electrons. When you guys say circuit, we said there must be a circuit, we're referring to a closed circuit. That's what you want, where electrons can flow through. You can imagine that there was a little switch here that went out like this, okay? That switch has now closed. It's going across this way, it's connecting that, and we have a closed circuit. That went out like for a complete circuit. The path, our closed circuit, the path is complete. The switch is closed. It's in the on position. Now, if I were to open, if let's say I had a little switch here, and I were to open that switch, and there was no wire in here, this was all just white, I would have an open circuit, an incomplete path for electrons. The switch is open. It's in the what position? Off. Yes? How you press the what? Oh, yeah. I'm calibrating it so it knows where I'm trying to write. Did you notice how it was a little bit off? So I fixed that. Okay? So this is an open circuit. Again, we wouldn't have anything here. if I were drawing this as an open circuit. There'd be nothing here. It'd be like the door's open, you're letting all the heat out. The electrons cannot flow back to the other side. If they can't get to the other side, we don't have a circuit, we don't have light. Right now, are these switches in the open or closed position? Closed. Closed means the circuit's on. Open, the circuit's off. Okay? Now, a lot of times, people that are getting new to electricity, they confuse something. They misunderstand the difference between an open and closed circuit and what we call a short circuit. And I see this done quite frequently. I see students, turn on a light bulb like I have here. So I've got my batteries, I've got my supply that runs through the bulb and back to the other side of the battery. And I say, find a way to turn it off. And they do this. They take the two battery connections and they touch them together. And lo and behold, the light goes off. Well, what have we made here? A short circuit, an easier path. That would be the same as if I were to take a wire and connect it across here. Now, you think like the electrons. Electrons are always going to go what direction? Forward. Their goal is to get where? Opposite side of the battery. They will take the path of least resistance. So here you are, little electrons going to go through this circuit. You reach this point. You have two choices. Option A, you can go through this nice thick wire and straight to the other side. Option B, you can go through the tiny little filament here of both bulbs to get to the other side. Which are you going to choose? The thick wire. A. Okay? This is the easier path. All the electrons would go this way. None of them, zero, would go that way. Now do you see why the bulb goes out when I do that? I've created a little shortcut, and people mistake the shortcut. They think the short circuit means shorter. It doesn't always mean shorter. When I do that, yes, the bulb does go out, but that doesn't always have to be a shorter path. Remember, it's the path of least resistance. So imagine now that my short circuit looks like this. Here's my wire connecting here, and it goes over here, over here, like that. What do you think it's going to do? What are the electrons going to do? Are they going to go down the green wire, or are they going to go through the two bulbs?
Green wire.
They're still going to go through the green wire. The wire is an excellent conductor. It's thicker and an easier path than these tiny little filaments. Even though it is longer, and you're right if you remember that the longer the wire, the greater the resistance. But guys, if it's a thick copper wire like the ones we're using here, it would have to be super, super long before it would be harder for it to go through here than through the bulb. That little bulb filament is so tiny that for the electrons to go through these bulbs would be like you driving to Phoenix by going up over the Catalina Mountains and over the Rincons and over the Santa Ritas and then back around and to Miranda and then to Phoenix. Okay? It is so much harder to go through that tiny little filament than it is to go through a wire. So a short circuit would be the way it would travel. Yes?
Well, how would they know that this was like a light bulb?
How would they know that there's a light bulb up ahead?
Yeah, like.
Well, remember that when I described the flow of electrons, I've been using water and you're imagining in your head water flowing through. But in reality, electrons don't flow like one little electron zipping through here, okay? It's more like when I had you guys stand up here to simulate the flow. Do you remember this? I described the electron flow being like what? Setting up what? No, I had like 4 people and I had their hands on each other's shoulders. Remember that? Dominoes. Remember that? It's like dominoes. But if you imagine the people I had lined up with their hands on the shoulders of the person in front of them, okay? If person number 4 at the end, let's say the electron's right next to the light bulb, if they're resisting, person number 3 is also going to have a lot of resistance, right? Person number 2 is. So way back here, I can feel that resistance already. And that means everything's affected. Everything in that circuit's affected by those things. If, however, I have another path, I'm pushing two lines of people. This one, they're all resisting. This one, they're not. I'm going to go right through that way. I know from the very beginning. Does that make sense?
Yeah.
Okay. So that's a short circuit. Now, is a short circuit what we want to use to turn off the lights? No. I could go over here and I could stick a wire in the outlet and I could short things out. And what would I get if I stuck the wire in the outlet like that? Okay, a big shock, could die. What else? Yeah, what else would be produced though? Are the electrons doing anything when I create a short circuit, when I touch those two wires together? What are we making? Heat. Okay, a short circuit, I'll give you the definition for that now, is an easier, undesired path for electrons. An easier, undesired path for electrons. We don't want a short circuit. It can be dangerous and produce sparks and heat. It can be dangerous and produce sparks and heat. An undesired path for electrons. We don't want to turn out the electricity that way. The electrons are going through, they're completing their path. If I run a wire across here, but that wire and the battery are both going to heat up because there's so much flow. I've made such an easy path now that all the traffic goes down that wire. Okay? One year I was doing a lab, this was before I got to electricity, and explained just how dangerous electricity was. And there was a student in the back, and I'm watching them like I do, and I listen to your little conversations that are often interesting. And that student was going, what the heck is going on back there? And he had a paper clip, and he thought this is how he's getting his jollies. Sticking the paper clip into the outlet. Okay? All I can say is I hope that student didn't go on to reproduce, because that's not the smartest person in the world. Okay? You may have accidentally experienced an electric shock before. Being careless, putting a light bulb or something, I don't know. I have my own story about that. And you may have survived it and thought, oh, electricity feels funny, it's kind of cool, but it's not going to kill me. I don't believe what they say. It takes less than 1 amp to stop the human heart, 1 amp of flow. Okay? A 120 watt light bulb uses 1 amp. Okay? That's more than enough to kill you. Those outlets, depending on what circuit breakers hooked up to the outlet, might supply anywhere from 10 to 30 amps. More than enough to kill you. Sometimes you luck out. Sometimes the electricity doesn't flow through your heart and stop your heart. It just shocks you. Sometimes it causes your muscles to seize up and you hang on to those wires and you can't let go. And you get electrified. Okay? People die all the time from not respecting electricity and what it can do to you. So we don't want to use a short circuit to turn things off. Everyone should have now schematic, open circuit, closed circuit, and short circuit. All we have left to talk about are the relationships. And when I talk about relationships, I'm talking about between the parts. And let me give you an example. You guys know the term relationship. Patrick was talking to me before class about his girlfriend. Remember the girlfriend you were telling me about? The supermodel in Canada that you're dating right now?
Oh, baby.
Yeah. So Patrick claims to be dating this supermodel in Canada. He kind of forgot her name for a moment there, but says that there's this beautiful girl. She lives in Canada. She's a supermodel, and that's his girlfriend right now. Well, we all know for there to be a relationship, there has to actually be how many things? A minimum of 2. Okay? You can't be in a relationship if it's just an imaginary girl in Canada. There has to be an actual another human being. Then you can have a relationship. Okay? In order to have a relationship here, I have to have 2 parts. So now what I'm going to do is I'm going to describe what's the relationship of one part to the other. One part to the other. And when I say relationship, I mean how do they relate to each other when it comes to the battery, to the supply of electricity? What do they do? Do they have to share it? Do they get their own supply? And when you understand the rules that govern series and parallel circuits, you'll be able to make all sorts of predictions. Now, based on just those words alone, what kind of circuit do you think this is? Series or parallel? Go ahead, take a chance, guys. It's 50-50. Series or parallel?
Series.
Series. How about this one?
Parallel.
How about this one? Series and parallel. Okay, I'm going to give you 3 different ways of identifying which one they are. And they're all useful to know. And then I'll give you the definition here in a little bit. Okay? You know the word series. You watch a TV series. Lost. It's on every Wednesday at 7 o'clock or whatever. On the same channel. Unless there's a writer's strike. Okay? And then you get to watch reruns. So every week you tune in at the same time on the same channel and you watch your show. One after the other. That's where that word series comes in. A serial murderer is not someone that goes around drowning people in their breakfast cereal, okay, or killing them with cereal. It's serial with an S, not a C, and that means in a row. They kill somebody and then another person and then another person in a row. So now you can start to see why this is called a series connection, because as the electrons flow through here, the parts are in a row. I would describe the relationship right here as series. You're in a row, one after the other. This row compared to this row, I would describe your relationship as parallel. Now think about this for a moment. I'm the pizza delivery man. I give you a pizza, I give you a pizza. You get your own. You don't have to share with him, he doesn't have to share with you. But you guys all have to get from them. So you take your piece, pass it back. You take your piece, pass it back. Does this make sense? Everyone that's in a row like this, they have to share their piece of the pie. If you got your own row, you don't have to share with the other row. And if you're the only person in your row, you get the whole thing, right? If you're the only person in your row, you get the whole thing. So this is called a series connection, and there's several ways you can check for this. First thing you're looking for in a series connection is you look at the parts. I'm asking you the relationship between L1 and L2. And you ask yourself, does one have to go through the other to get its supply of electricity, of electrons? Okay, the electrons can flow to this one, no problem. There's nothing in the way here. There's no other part. But every device needs at least 2 wires to it to work. Look at the other wire. It must go through another part in order to be connected to the other side of the battery. Do you see that? So if this were water flowing through here and I were to squeeze on the pipe right here, would that affect the flow to this one? Yes, it would. Okay? Because they share. This one has to go through that one to get back to the battery. Same thing is true for this one. It has one of its own lines back to the battery here, but the other line has to go through another part to get back to the other side of the battery. They share that voltage. They're going to share that. Now, what do you think would happen if I were to just pull out this light bulb? Leave blank white space there. What would happen to L1? Well, let me do it here for you. So I'm going to create a circuit here. 2 light bulbs in series. Sorry I'm boring you. Now I know it's probably hard to see with the light there, but are they lit? Yeah, they are lit. And if I take out one bulb, what's going to happen to the other one? It's going to go out. That's a second way you can determine whether or not they are in series. So you can look at the arrangement, you can trace the path back, you can take one of the parts out. If you take one of them out and the other one goes off, you know they're in series. In real life, what kind of device works this way? Christmas lights. One bulb goes out and a whole chunk of the string goes out. That tells you that all those lights are wired up in series. Okay? You take out one, the other one's going to go out. So that's another way to test for it. Now, if I have 10 volts here, predict what the voltage is going to be here at L1. Remember, if I give a pizza to Marissa, she has to share it with everyone in her row. 5 people in her row. There's 10 slices, they each get 2. These are all in a row. It's going to go through this one, it's going to gobble up some first, and this is going to gobble up some. The bulbs are identical. They have an equal appetite. What's the voltage going to be on L1? 5. What's it going to be on L2? 5. Will the bulbs be bright or dim? Do they get the full 10 volts? No. So are they going to be bright or dim? Dim. That's a series relationship. Okay? Now we go over here to this one, and we have what kind of relationship? Parallel. Now here's the mistake a lot of students make. They look at the wires here and they go, oh, well, I got this figured out. Duh. They're all in nice straight parallel lines, therefore it is parallel. Can't always do that. Lines don't always have to be straight up and down like that. In fact, I could draw that wire and have it go woo all over the place and come back here. And the wires may not look parallel. What you have to do is trace the flow back. In this one, when I trace the flow for both sides of that light bulb back to the battery, one of them has to go through the other one. That's why they share. On this one, I traced the path back, didn't go through another part. Did you see that? I traced the flow back. I didn't have to go through another bulb to get back to the battery. That's what makes them in parallel. Now I'll hook that up here. And I want you to predict, will it have the same brightness? Will the two bulbs be the same brightness as you saw over here? Here's Marissa's row, here's TJ's row. Nobody's in their row. They both get their own pizza. Will they be as bright as they were on A, brighter or dimmer? Brighter. If you predict it brighter, you're right. Now you can see, and you can clearly see those. Woohoo, yeah. Because they have their own path back to the battery. They don't have to share that voltage. You know, your neighbors flush their toilet when you're in the shower. It's not going to make the water cold for you. It's not going to affect you because they get their own supply. You got your supply, they got their supply. See what I'm saying? You don't have to share. Now on this particular circuit, a parallel circuit, what do you predict is going to happen if I were to remove this bulb from the holder? Will the other one go out or stay on? It stays on because it has its own path all the way back to the battery. So that's another test for whether it's in parallel or series. Okay? All right, let's look at this third one now. How many think they understand this so far? Okay, well, if you really do understand, you'll be able to tell me then. If this is 10 volts here, L1 will have, and L2, 10 volts. They don't have to share, which is why they're brighter over there. This last one, now it gets a little more complicated because we're not just talking about two things, we're talking about three things. So you have to follow a few rules. And if you just remember these couple of rules, you'll be able to predict what's going to happen. Would you shove the person behind you there, Anthony? I don't want to say her name on the podcast, but I don't think she's totally awake. Okay, can I see your face? I can't even see your face. Thank you. Now we have more than one thing. So if I ask for a relationship, I need to be very specific. I might ask you for the relationship of L1 and L2. I want to know how they're related to each other. I'm sorry, L3. L1 and L3. Thank you. And if I ask you the relationship between these two, I don't really care about this one. You know, I want to know the relationship between Megan, Lynn, and Marissa. I don't care about the rest of the class. Sorry, don't take it personally, but you don't matter. Just those two. So what I do is I just ignore this one. I pretend it's not there, it's just a wire, okay? If I do that, what would you say the relationship is between these two? You would say they're in parallel, right? If I want to know the relationship between L3 and L2, you would ignore this one. Now, we can't pretend that it's a wire because that would make it a short circuit. Do you see that? So we just pretend this whole part here is gone altogether. What would be the relationship here then? Series. But I can get even more complicated. Now I can treat things as groups. I can ask you to tell me the relationship between L1 and L2, L3. L1 and L2, L3. You're going to treat that like one bulb. Now if that were one bulb, and this is the second one, what would the relationship be? Can't seem to agree.
Parallel.
Well, let me ask you this. Let's look up here. If I were to take this bulb and move it up here, what would the relationship be between these two? Would it still be parallel? Yes. It doesn't matter that it's up here. You do see that, right? Just because it's here, or here, or here, or here, or here, doesn't change the arrangement. It still has its own wires back. Okay? If I were to eliminate all of this and put the bulb here instead, what would the relationship be? Series. Because then they would share a path back to the battery. Okay? So all we're doing is the same thing I just described. We're combining these into one. So what's the relationship between L1 and L2, L3? Parallel. If you said parallel, you're right. How many are getting this? Because I feel like I'm losing some of you. If you know that, if you can tell me if it's series or parallel, you can predict the voltage. Let's look at this now. If I have 10 volts here, how much am I going to have at L1? 10 volts. It has its own path back. It gets the full supply. So that's Marissa's row. She's the only one in her row. Everyone else is sick that day. In TJ's row, there's two people. Two people in his row. You see that? In his row. So I'm going to treat this as one thing right now. Combine these together. What is the pair going to get? How much voltage is the pair going to get? How many say 5? How many say 10? Those of you that said 10 are right. The pair, the two together, get 10 volts. If we treat this as one, you said the relationship was parallel, right? Well, when they're in parallel, don't they get the same thing? So 10 volts here, 10 volts for the pair. Now we look inside the pair. And we say the relationship between these two is series. Well, if I give the pair 10 volts, but the two are in series to one another, how much does L2 get? 5. And L3? 5. Do you see how as a pair they're getting 10? Okay, they have to share that 10, but they do get 10. So you can figure out exactly what the voltage should be. And you can predict that this one's going to be bright or dim. And this one's going to be, and this one's going to be. And if I were to remove L3, for instance, what would happen to L2? It would go out. If I were to take this out, there would be what kind of circuit there? If I were to remove it from the battery holder and leave an empty space there, what would happen to L2? It would go out. What would happen to L1? It would stay the same. It wouldn't change it. If I were to remove L1, what would happen to L2? Nothing. What would happen to L3? Nothing. A lot of people predict if I take this one out, these two will get brighter. They don't, because they're still in, what's their relationship to each other? Series. They still have to share. It doesn't change it. It confuses you? Think of it this way, okay? If you imagine this is like a loop with water flowing through it, okay? You know, in your neighborhood, water comes down, a main water supply, and it goes off to your house, and to the neighbor's house, and the next one's house. And when they turn on their water, turn off, it doesn't affect you. You have your own supply back to the main line. If I were to squeeze on this wire right here, okay, and I were to add resistance, I were to put something in here, that's going to affect the flow of anything that has to go through that. Okay? So if I put, let's say, a light bulb right here, is that going to affect this one? Well, let's find out. Got one path back, doesn't affect it, won't slow it down there, but will it affect this one? Yes, it will. That'll slow it down. Would this also affect L2? Yes. Do you see now what's happening? When you don't have anything blocking your path back, you get the full supply. Now, it doesn't mean you're getting something for nothing. This is going to use a lot of current, but it's going to burn brighter if we hook them up in parallel, like you see there. Okay? Series, they're going to have to share that. It slows it down. I squeeze on the wire here. It affects everything in that loop. This is doing the same thing. It's putting resistance. Now, it's not squeezing on a wire because the wire is not hollow. It's not carrying water. But it's doing the same thing that you would have if this were a loop of water. How many think they understand this? Great. Okay, we don't have a lot of time. I just wanted to give you the opportunity to try this out if you'd like to, you can answer these questions without having to do the lab. In fact, we have answered all of them. If you want the definition for series and parallel, I am going to read them out to you here in just a second, but they are at the top of this page. In the series relationship, electricity has to flow through another device to get back to the battery. It must flow through another device to get back to the battery. We would say they share the voltage. In a parallel circuit, it's just the opposite. It doesn't have to go through another device. They don't share the voltage. Series, they do. Parallel, they don't. Series, you go through something else. Parallel, you don't. Okay, Sky, you're 1. Anthony? 2. 9. Oh, I'm sorry, you're right. 1. 3. 5. 7. 1. 1A. 1.
5.
6. Okay, I want you to write those numbers in the upper right-hand corner of this because you're going to be at those same stations tomorrow. If you want to go to that station today to help work through those questions, you can. You don't have to. This just helps you test it out and see if you are right, if your predictions are right. Number 1, 7, 8, 9, and 10 don't have to be in complete sentences. The others do. Number 1, 7, 8, 9, and 10 do not have to be in complete sentences. The others do. If you wrote a sentence, that's fine. I'm not going to penalize you for it. If you want to go to your assigned lab station to help work through those, you can. You don't have to. If you want to stay at your seat, you can as well.